The second algorithm that we look at in terms of meta-learning is MAML, and more specifically we will also look at its implementation of ProtoMAML, which really combines the protonets we have seen before with MAML. MAML is short for model-agnostic meta-learning and is an optimization-based approach compared to protonet, which basically is more metric learning approach, meaning that it compares images from the support set with a query set, while here we actually try to optimize, so fine-tune our model on the support set, so directly the parameters. The idea here is then that given basically our model, we will now take a small support set and really do SGD on our parameters on the support set. And after a few steps, we evaluate then this network on a new query set and then do backpropagation to the original parameters. That already shows you that we now actually need second order gradients, meaning that we need gradients through gradients, which makes this approach more complex and also more computationally expensive. Therefore, there are also strategies to do it only with first order gradients, and this is actually also what we will do here, which is called first order MAML, which is therefore more efficient and has also shown to almost get the same performance. MAML then here, if you just look at the visualization above, that is kind of, so we have given theta at a certain point, and what we do is we then perform for different support sets their optimization. So if we have given 3 different support sets, or let's say we have 3 batches, one batch might optimize our parameters to theta 1 star, another one to theta 2, and another one to theta 3. And from those, we get all the gradients and combine them together. So you can already see we now have a 2-stage of batches, namely that we have a batch of images per support query set, and we actually have now also a batch of tasks, so that we actually sample a batch of support query set pairs. This is because that really helps you to then not just optimize always for one specific support and query set, but rather have a more smooth training curve, which is really beneficial. This you can also see here in just the algorithmic form for MAML. So what MAML basically does is we start with a random theta, we sample then a batch of tasks, and for each task in this batch, we sample then a support set on which we learn, and we also use then a query set down here to then evaluate our fine-tuned model below then. Therefore, then this update of original parameters of our thetas are then the sum over the losses for each of these individually fine-tuned models. And there, in this update step, we would need the second order derivatives because there's a dependency between theta prime and theta through actually having gradients based on theta as well. ProtoMAML now takes one disadvantage or one problem of MAML away. Namely, in MAML, just imagine we now have different sets of classes every time. So now, for instance, one task has a classification of 5 classes, another task has maybe 4 classes, another one has 8 classes. In MAML, that becomes difficult because we have one model that performs simple classification, meaning that the output layer, this layer that takes from the final feature vectors to the class dimension, would need to be fixed, or is basically also again learned, and would therefore be needed to reinitialize every time we train. And this is often a very expensive part just of training, because the main network might not need to be fine-tuned too much on the new support set, but rather only the output classification layer. And ProtoMAML then comes with the idea of saying, okay, we already have seen from Protonet how we can use prototypes actually to classify, and you can just reformalize the softmax into a matrix product, which is shown below here. And this exactly resembles our basically a linear layer. Therefore, what it does here is to say, okay, we can take our support set, calculate the prototypes of this support set with our network, and then use these prototypes to initialize our output layer, which does our classification. And then with this initialization, we can perform our classification. We have basically just taken a step ahead. Instead of initializing our output layer with zeros or with random values, we just have already values that go very much into that direction. That helps not only in efficiency, but also just with training in general. Now we can look at ProtoMAML as its implementation. So you will see that the implementation looks quite complicated, and this is because we do both in the sense of first order gradients, so we do not use second order gradients for efficiency, and ProtoMAML also needs now to adapt the batch sampler that we had before, because we now need to sample a batch of tasks, so meaning a batch of support and query set pairs. This is something we will then check later, and first we assume that we have given these batches and now try to implement ProtoMAML here as a PyTorch Lightning module. So we start again, we just have our standard model as before, and in our general loop here, so basically our training step, if we have given a batch, we run what is called the outer loop, and the outer loop first does for each task in our batch, we take again our images, we split it over support and query set, and then we adapt, so we fine-tune our model on this support set and our basically our support images and its labels. And this gives out a new model, because this now just has its, our model here, our self.model, as initialization, and adapts it to this specific support set. And this we will then use to apply our model to and get a loss back. And this loss we perform a backward and sum the gradients of this local model with the gradients of the global model. So basically just sum up the gradients of all the task batches in this local model gradients, and then use that finally to do a step in our optimizer. So that might first look a bit complicated, but now let's go into the details of each step. So how do we perform this few-shot adaptation? We have given a set of support images, we have given a set of support labels. We first again run our model just to get the features and calculate the prototypes so we can initialize our output layer with it. Then a step here, which is needed for our first order gradients, is namely that we take our initial model and duplicate it. This is because we don't want to forget what our initial parameters were and just want to create a copy of it on which we can then fine-tune with standards, for instance here SGD methods. We use here the prototypes to initialize our output layers weight and biases, and then what we just do in this loop, which is then called the inner loop because it's an inner optimization loop with our support set, we take just, or we run our model, our local model, with our output layer on the support set, and just do standard loss.backward, a step, and then set everything to 0 in terms of gradients. Afterwards, after we have optimized this for a few steps, we need to do a small trick because we want to do first order gradients. So first order gradient just approximate the second order by saying our local model has the same parameters as the initial one. So it just calculates the gradients as if the local model would use the same parameters. But we also allow to actually flow back gradients through the prototypes to the original network. So this is what this small line does. It does nothing else than adds our prototypes back into the computation graph. So if we now apply our model to our query set, what we do there is then we have a computation graph to the original model, to the original global model, and to our local model, and therefore get the gradients of both with respect to the prototype initialization and the fine-tuned model. So this is needed to do a approximation here of first order gradients. This is the adapting of few shot, and the one model is then nothing else than just applying a model performing a linear layer and then the cross entropy loss to calculate our standard loss and therefore get gradients. So this might look all a bit more complicated. I recommend just to go through the code where you solve like step by step to really see what we need to do to get these first order gradients and have efficient running of a model. However, you can also already imagine that this might take now longer than ProtoNet to train, because we need to copy the model all the time, and once you have fine-tuned your model and got the gradients, you can delete it again. So the training, what we do now is we have to first define our task batch sampler, right? That just uses our few-shot sampler and collects just multiple batches of it. So this is kind of what we do here. At each step, we just ask the batch sampler to return a couple of batches and then return a batch of batches. And that we also then combine these batches into one set of tensors that we can then return to our model. Again, here we just define our training and validation set and then can start training our model. You can see here again a lot of hyperparameters. Ones that are very important are usually the number of inner steps. This is the number of steps we take in the inner loops. So how many SGD update steps do we take on the support set? If we use ProtoMAML, this number can be often very small. So here, for instance, we just use 1. However, if you use standard MAML, you need more steps because you need to also optimize the output layer initially. But I highly recommend to also do a hyperparameter search over these number of inner steps, because if you have more diverse, more different tasks, you will need more loops in your inner, or more steps in your inner loop, because you need to really fine-tune your model more on the new set. As we just do classification over a similar set of images that are all coming from Cypher, we experience that often very few steps are important. Now that we have trained, we can also look at the tensor board to just give you a bit of an intuition of how this training looks like. If we go, for instance, to the training accuracy, we see it is a bit smoother than ProtoNet, but this is also because we have a batch of tasks on which we optimize our model, but the training time is also quite some longer. So don't be surprised by just seeing about 14,000, 15,000 update steps. This is still the same number as on ProtoNet, but we always collect first a batch before we do updates. Right? Therefore, even these 15,000 steps took about 8 hours on a strong GPU to do. Validation seems also similar as on ProtoNet, only slightly smaller. The testing of this model works very similar to ProtoNet. We simply do it really in the same way. We take our test set, split it into support sets, and use those to fine-tune our model and evaluate then on all of the rest of the images, or basically the rest of the data in our setting. A difference between the testing and the training of ProtoMAML, or also MAML in general, is that during testing it can help a lot to actually increase the number of inner steps. So we don't just take one fine-tuning step, but actually take a lot of them. You can also imagine that if you just take a lot of steps during training, it's much more expensive to first backprop if you would use second-order gradients, and it gets less accurate if you would just take first-order gradients, because then you just take, or your approximation gets worse and worse the further theta and theta prime get apart. Let's look at the results. A difference when in ProtoNet is that we don't do it here in Colab, but instead provide you with the results, because it can take quite some time. And you see that the results are quite similar to ProtoNet, only that we are able to outperform ProtoNet slightly on larger sets, because we now allow also the model to fine-tune. Right? You can already see that if we have given more data, ProtoMAML can have an advantage over ProtoNet simply by allowing us to fine-tune the model. there you can already play around a bit more to see what the differences might be. Finally, let's try to test our models actually on a more challenging setting, namely when our test set or test images are not from the same pool of images that we have trained on. So we have trained on Cypher 10 or Cypher 100 images, but what if we now test this model actually on a very different domain, namely here, for instance, the street view house number dataset. So this is a real-world dataset with these images shown below, where you basically have to recognize now numbers. That is quite different from our training, but this is also what meta learning is supposed to do, right? It is supposed to learn to learn. Of course, we do here a very drastic differences because we didn't really train the model to adapt across multiple domains, but we can still see how well it can adapt now to a different setting. Let's first create this dataset. So this dataset has basically 0 to 9 as classes, and we limit our dataset by giving it 500 images per class, so we can perform better meta learning or evaluation on them. What we first do is we take our ProtoNet and apply it in the same way as before, now on this new dataset. So we take again our images, push it through our model, and then use this prototype classification to classify our new examples in the query set. This goes again quite fast, so we can do it here directly in Google Colab Live. And you see that the results are quite worse than we had before, simply because the images are very different. So from k equals 2, if we have given 2 classes or 2 images per class, we get only slightly above random accuracy, while with 32 images we are getting better, but actually not where we would expect it to be. Let's try it with ProtoMAML, and there we see actually a big difference. So let's also maybe plot it, which can show a better difference in here. Specifically, with the more data we have, the better ProtoMAML becomes, because we can fine-tune our model. Right? We can fine-tune now actually our underlying model, which therefore allows ProtoMAML to really get a big advantage over ProtoNet, which can just always, the more data it becomes, the more accurate maybe the prototypes get. But if the features do not represent any good actual description of the images, the classification can also not improve. And thereby ProtoMAML can help to just use these prototypes as a initialization, as a good starting point, but can optimize the model to actually become better and better, and therefore can reach better classification accuracies than ProtoNet in this setting. This brings us then also to the conclusion. So what we have seen in this notebook is basically how we can perform meta learning, how we can learn an algorithm to learn and quickly adapt to a new setting. We have looked at the different algorithms, ProtoNet, MAML, and ProtoMAML. We basically implemented ProtoNet and ProtoMAML. On this few-shot classification task, where you really saw that ProtoNet and ProtoMAML basically perform similarly well. But if you go to a different domain, so very different sets on which you trained, ProtoMAML can just get basically ahead of ProtoNet by this ability of fine-tuning your model. This you can also then see if you just train on a much more diverse set of tasks. So let's say, for instance, in natural language processing, you would actually train on very different tasks like text classification or metaphor detection or pronoun resolution. That is all very different tasks where you might have to fine-tune your model to focus on different aspects of the text of the input. And there ProtoMAML is expected to really outperform the simple ProtoNet, but ProtoNet on the other hand is just very efficient. So if you just have a task where you know you could easily or that your ProtoNet is sufficient for it, then you should just go with it because it's much more efficient than ProtoMAML. Still, there's probably much more to do in the research, and all of the algorithms also need quite some hyperparameter tuning. Therefore, meta learning is currently still often quite expensive in computation.